Picture the darkest corners of the universe, not empty, not silent, but blazing with beacons so powerful they outshine entire galaxies. These are quasars, the cosmic lighthouses that pierce through the void, defying everything we thought we knew about the laws of physics. Their brilliance is so immense that if you placed one where our sun sits, it would vaporize Earth in an instant. Yet, these celestial monsters are more than just dazzling spectacles. They're windows into the most extreme, bizarre, and downright mysterious phenomena in existence. What if I told you that some quasars shoot jets of matter at nearly the speed of light, stretching across millions of light years like cosmic blowtorches? Or that their hearts harbor supermassive black holes so dense they warp space and time itself? But here's the real kicker. These active galactic nuclei, or AN, don't just break the rules. They rewrite them, from flickering like cosmic strobe lights to emitting energy bursts that could power civilizations for eternity. Quasars are the universe's ultimate enigmas. And today, we're diving deep into 25 of their most mind-bending secrets, phenomena so strange they'll make you question everything you thought you knew about space. This isn't just a journey through the cosmos, it's a descent into the unknown where the laws of physics twist into knots and reality itself seems to unravel. By the time we're done, you'll see quasars not just as distant lights, but as the universe's most dramatic storytellers, revealing secrets about black holes, dark matter, and even the fate of everything. So buckle up, we're about to explore the impossible, the inexplicable, and the utterly breathtaking wonders lurking in the hearts of these cosmic titans. At the heart of every quasar lies a monster, a supermassive black hole so ravenous it devours matter faster than any cosmic phenomenon we've ever seen. Picture a whirlpool, but instead of water, it's a swirling disk of gas and dust, heated to millions of degrees, so bright, so violent, it outshines entire galaxies. This is the accretion disk, the cosmic buffet where gravity's grip tears apart anything that ventures too close, and the way these black holes feast defies logic. Normally, black holes grow slowly, nibbling on stray stars or gas clouds over eons. But quasars, they're the ultimate gluttons, consuming the equivalent of our sun's mass not in a million years, not in 1,000, but in a single day. The physics behind this feeding frenzy bends reality. Matter spirals inward at nearly light speed, colliding and compressing until it glows with the fury of 100 trillion suns. The friction alone generates temperatures so extreme that particles are ripped apart, radiating energy across the entire electromagnetic spectrum, X-rays, gamma rays, light we can't even see. What's truly bizarre is how this process challenges everything we thought we knew about black holes. Einstein's equations suggested they should grow at a steady pace, constrained by the speed of matter falling in. But quasars laugh at those limits. Some appear to have bulked up to billions of solar masses when the universe was barely 1/10 of its current age. How? One theory points to chaotic mergers, galaxies colliding and funneling entire rivers of gas straight into the black hole's maw. Others suggest magnetic fields act like cosmic conveyor belts, slingshotting matter inward faster than gravity alone could manage. And then there's the disk itself, a place where time and space twist into knots. Close to the black hole, time slows to a crawl. A single orbit for a speck of dust might take seconds for the particle, but centuries for an outside observer. The energy released is so immense, it doesn't just light up the cosmos, it pushes back, creating winds powerful enough to blow apart nearby star systems. This isn't just a black hole eating. This is a black hole feasting, and in the process rewriting the rules of astrophysics with every bite. But the cosmic spectacle doesn't end at the black hole's edge. As matter spirals into oblivion, some of it escapes, launched into the void not as a whimper but as a scream. These are relativistic jets, narrow beams of plasma erupting from the quasar's poles at nearly the speed of light. Imagine a cosmic fire hose blasting particles with such force they could cross our solar system in less than a day, and these aren't just fleeting bursts. Some jets stretch for millions of light years, far longer than the galaxies that birthed them, carving through space like interstellar lightning bolts. What makes these jets truly bizarre is how precise they are. They don't spray chaotically in all directions. Instead, they align almost perfectly with the spin axis of their host galaxy, as if some invisible cosmic compass guides them. Scientists think this alignment traces back to the black hole's rotation, which twists magnetic fields into a focusing funnel. Picture a spinning top wound so tightly it flings off energy along its poles, except here, the top is a supermassive black hole, and the energy could power a star for millennia. Even stranger, these jets don't just race through empty space. They plow into galaxy clusters, heating gas to millions of degrees and sculpting vast bubbles in the intergalactic medium. In some cases, they act like cosmic trowels, preventing new stars from forming by blasting away the raw material needed for stellar birth. Yet in others, they might trigger star formation by compressing gas clouds in their wake. It's a paradox: destruction and creation woven into the same violent thread. The energy involved is almost incomprehensible. A single jet can outshine its entire host galaxy in radio waves, and when these beams slam into surrounding matter, they generate shockwaves visible across the cosmos. Some jets even flicker unpredictably, as if the black hole is coughing out matter in fits and starts. And here's the real mystery: we've never directly seen the moment these jets are born. The region where they launch, just outside the black hole's event horizon, is so small and distant that even our sharpest telescopes glimpse only blurred hints. Theories abound. Maybe magnetic fields act like particle accelerators, slinging plasma outward at impossible speeds. Or perhaps the black hole's rotation twists space-time itself into a slingshot. What's certain is that these jets are more than just cosmic fireworks. They're clues hinting at how black holes shape galaxies, how energy flows across the universe, and how even the most violent processes can weave order from chaos. Now imagine a cosmic light bulb flickering not over years or centuries, but in mere days. Some quasars don't just shine steadily. They pulse, dim, and flare with bizarre unpredictability, as if their immense power sources have a cosmic short circuit. This isn't just a flicker, it's a full-scale rebellion against what scientists thought possible. Here's the problem: quasars are powered by accretion disks so vast they could swallow our solar system whole. According to physics, something that large should change brightness slowly, like a bonfire fading over hours, not a strobe light flashing in seconds. Yet some quasars defy this logic, swinging from dim to dazzling in less time than it takes Earth to orbit the Sun. The implications are staggering. Either these disks aren't as large as we thought, or some hidden mechanism, some cosmic sleight of hand is at work, compressing these changes into impossibly brief bursts. One leading theory points to hotspots, temporary, ultra-bright regions that ignite like flares on the disk's surface. Picture a spinning pizza crust with chunks of molten cheese bubbling up at random, each one briefly outshining the rest. Magnetic instabilities might twist the disk's plasma into knots, creating these localized infernos. But even this explanation strains credibility. For a quasar's brightness to double in days, these hotspots would need to span tens of astronomical units, far larger than any known stellar phenomenon. Another possibility: the disk isn't a smooth, flat plane but a turbulent storm of clumps and filaments. Collisions between these chaotic structures could release energy in erratic spikes, like boulders tumbling in a cosmic avalanche. Or perhaps the flickering comes from deeper within, some instability near the event horizon itself, where gravity's grip warps the very fabric of space-time. What's truly unsettling is how these rapid changes challenge our understanding of causality. If a quasar's core does flicker in days, it implies the emitting region must be smaller than the distance light could travel in that time. Otherwise, the signal would smooth out like blending ripples in a pond. Yet supermassive black holes should be too large for such tight timescales. The math simply doesn't add up unless we're missing a fundamental piece of the puzzle. And then there's the wild card, microlensing. Could intervening stars or black holes floating unseen between us and the quasar magnify and distort its light like a funhouse mirror? It's possible, but these events should be rare, yet quasars flicker frequently, suggesting the culprit lies not in front of them, but within. This variability isn't just a curiosity. It's a clue whispering that accretion disks might be stranger, more dynamic realms than we ever imagined. Perhaps they're riddled with magnetic tornadoes, or maybe the black holes spin cracks spacetime like a whip, sending shockwaves through the disk. Whatever the answer, one thing's certain: the universe's brightest beacons are also its most enigmatic, blinking at us in code, daring us to decipher their secrets. The story of quasars took a dramatic turn in the mid-20th century, not with a discovery, but with a scientific civil war. When astronomers first detected these brilliant, point-like objects, their extreme redshift suggested they were racing away from us at unimaginable speeds, placing them billions of light-years distant. But not everyone bought it. A faction of researchers, led by the fiery astrophysicist Holton Arp, argued vehemently that quasars weren't distant cosmic beacons at all, but nearby objects ejected from galaxies with inexplicable properties. The debate split the astronomy community, sparking what became known as the redshift controversy, a battle over the very nature of reality itself. Redshift, for those unfamiliar, is the cosmic equivalent of a siren's Doppler effect. Just as an ambulance's pitch drops as it speeds away, light from distant objects stretches into redder wavelengths as the universe expands. The greater the redshift, the faster an object recedes, and the farther back in time we're looking. Early quasar observations revealed redshift so extreme they implied distances that defied belief. If correct, these objects weren't just far away, they were ancient, shining from an era when the universe was a fraction of its current age. But Arp and his allies pointed to peculiar galactic alignments, quasars that appeared suspiciously close to foreground galaxies, sometimes even connected by faint bridges of gas. How, they asked, could such associations exist if quasars were truly billions of light-years behind them? Arp's bold hypothesis: redshifts weren't always cosmic speedometers. Some, he claimed, were intrinsic, perhaps tied to exotic physics or even matter ejected from galactic cores like cosmic shrapnel. The implications were staggering. If true, much of modern cosmology, built on redshift as a reliable distance marker, would crumble. The controversy raged for decades, fought in academic journals and conference halls. Skeptics dismissed Arp's claims as cherry-picked coincidences, while his supporters highlighted anomalies that mainstream theory struggled to explain. The turning point came with painstaking observations of quasar-host galaxies. As telescopes sharpened, astronomers finally resolved the faint, fuzzy halos around quasars, proof they were indeed embedded in distant galaxies. Even more damning for Arp's camp, quasars were found clustered in ways that mirrored the large-scale structure of the early universe, not local space. Yet the debate left a lasting legacy. It forced scientists to question assumptions about redshift and confront gaps in their understanding. Today, we know quasars are the universe's most distant lighthouses, but the mystery of their extreme redshift still holds puzzles. Some quasars exhibit subtle anomalies that hint at unknown physics, perhaps interactions with dark matter or relics from the universe's birth throes. And while Arp's local quasar theory was ultimately disproven, his defiance reminds us, in science, even the wrong questions can lead to the right answers. The redshift controversy wasn't just a clash of egos. It was the sound of cosmology growing up, grappling with the universe's strangest children, and coming out wiser for the fight. The sheer luminosity of quasars isn't just impressive, it's obscene. Imagine a single object so bright it drowns out the combined light of every star, nebula, and planet in an entire galaxy. That's not science fiction, it's reality. Some quasars emit energy thousands of times greater than the Milky Way's entire stellar population, all while occupying a space smaller than our solar system. The numbers are staggering. The brightest known quasar, S50014+81, beams with the equivalent of 60 trillion suns, enough to outshine our galaxy by a factor of 600. How does something so compact produce such unfathomable energy? The answer lies in the chaotic dance of matter near the central black hole. Unlike stars, which generate light through nuclear fusion, quasars exploit gravity's raw power. As gas and dust spiral into the accretion disk, friction heats it to millions of degrees, converting mass into energy with terrifying efficiency. In fact, quasars operate at nearly 10% efficiency, far surpassing nuclear fusion's paltry 0.7%. That means for every bite of matter the black hole takes, it spits back a torrent of radiation capable of sterilizing entire galactic neighborhoods. But the real shock isn't just the brightness, it's the impact. These cosmic floodlights don't just illuminate, they transform. Astronomers now believe quasars play a pivotal role in galaxy evolution, acting as both creators and destroyers. Their radiation can blow away star-forming gas, effectively sterilizing a galaxy by shutting down stellar birth. Yet paradoxically, their shockwaves might also compress distant gas clouds, triggering new star formation far from the quasar's core. It's a cosmic push-pull, one that challenges our models of how galaxies grow and change. The implications ripple across time. Quasars were far more common in the early universe, suggesting they might have been the sculptors of the first galaxies. Their intense radiation could have reionized the cosmos, stripping electrons from atoms and making the universe transparent to light. Without them, the night sky might still be shrouded in fog. Yet today, most quasars are dormant, their black holes starved of fuel. What shut them off? The answer might lie in their own destructive power, blowing away their food supply until nothing remains to feed the beast. Here's the twist: we're seeing these objects as they were, not as they are. The light from distant quasars has traveled billions of years to reach us, showing us the universe in its violent youth. By studying them, we're peering into a time when galaxies were still taking shape, their fate swayed by the whims of these brilliant, destructive monsters. And that's what makes quasars more than just cosmic oddities. They're time capsules revealing how the universe forged order from chaos, one dazzling explosion at a time. The cosmic ledger appears to have a glaring gap, one that threatens to upend our understanding of how black holes grow. On one end, we've found stellar mass black holes, the remnants of collapsed stars, weighing in at a few dozen times the sun's mass. On the other, supermassive behemoths lurk in galactic centers, tipping the scales at millions or even billions of solar masses, but between them, a desert. Intermediate mass black holes, those elusive middleweights, should exist by the thousands, yet they're conspicuously absent from our observations. This isn't just a minor accounting error. It's a crisis for astrophysics, because quasars in the early universe demand that supermassive black holes grew fast, too fast, and without intermediate stepping stones, their origin story collapses like a house of cards. Think of it like trying to explain how a skyscraper appeared overnight with no construction crew. The youngest, most distant quasars, those shining when the universe was barely 700 million years old, harbor black holes already weighing billions of suns. But here's the catch: even if these monsters devoured matter at the maximum possible rate, they'd need seed black holes far larger than any stellar collapse could produce. Where did these seeds come from? Did they form directly from the collapse of primordial gas clouds in the universe's infancy, bypassing the stellar stage entirely? Or is there some exotic mechanism, a cosmic loophole, that allowed small black holes to balloon at impossible speeds? The math teeters on the edge of plausibility. One radical theory suggests the early universe was a black hole factory. In those first chaotic moments, dense pockets of matter might have collapsed directly into black holes without ever becoming stars, a process called direct collapse. These seeds, weighing thousands of solar masses from birth, could then feast on the abundant gas of the young cosmos, reaching quasar proportions in record time. There's just one problem: we've never caught these seeds in the act. Observations of the early universe show plenty of quasars, but their supposed progenitors remain ghostly silhouettes, vanishing every time we train our telescopes on them. Another possibility: black holes grew not by steady feeding but through violent mergers. In the crowded galactic nurseries of the ancient universe, collisions between smaller black holes might have stacked them like Lego bricks, rapidly assembling supermassive cores. Yet simulations struggle to make this work. Mergers take time, and the earliest quasars shouldn't have had enough of it. Worse, the gravitational waves from such crashes should leave ripples we can detect, but current observatories have found no smoking gun. The most tantalizing clues come from the rare intermediate mass black holes we have spotted, like the one lurking in the galaxy Messier 82, weighing in at around 400 solar masses. These stragglers suggest the missing link might not be missing after all, just hiding in plain sight. Perhaps they're cloaked in thick dust, or maybe they're dormant, their growth stunted by some cosmic intervention. The stakes couldn't be higher. If we can't solve this puzzle, our entire timeline of black hole evolution, and by extension galaxy formation, crumbles. Quasars are the universe's way of taunting us with a paradox. How do you build giants without the scaffolding? The answer might rewrite not just astrophysics, but our understanding of how chaos birthed order in the cosmos. And until we find it, the early universe keeps its most explosive secret locked away. Quasars do more than dazzle. They illuminate the hidden fabric of the cosmos itself. Think of them as the universe's ultimate backlights, casting brilliant beams through the darkness that reveal everything in their path. When their light journeys across billions of light years to reach us, it doesn't travel unscathed. Along the way, it passes through clouds of gas, dust, and even entire galaxies, each leaving its own fingerprint on the quasar's light. Scientists call these fingerprints absorption lines, and they're like cosmic barcodes, encoding secrets about the composition, temperature, and movement of matter we'd never see otherwise. Here's how it works. As quasar light pierces through a gas cloud, specific wavelengths get absorbed by atoms in that cloud: hydrogen, helium, or heavier elements like carbon and oxygen. Each element leaves a unique dark line in the quasar's spectrum, like a shadow in a rainbow. By decoding these shadows, astronomers can reconstruct the chemical makeup of the gas, its density, and even how fast it's moving toward or away from us. It's as if quasars hand us a layered map of the universe's history, with each absorption line representing a different era and environment. The real magic lies in the sheer depth of time these observations cover. A single quasar spectrum might reveal gas clouds from when the universe was less than 2 billion years old, alongside others from just a few 100 million years ago. It's like finding fossilized layers in a geological dig, except instead of rock, we're studying the primordial soup that birthed galaxies, and the surprises keep coming. Some absorption lines hint at vast reservoirs of invisible matter, far beyond what stars alone could account for. Others show gas so pristine it's barely changed since the Big Bang, untouched by the polluting forge of stellar explosions. But quasars don't just catalog the universe's ingredients, they expose its structure. The patterns of absorption lines reveal a cosmic web, a sprawling network of filaments where gas clumps into galaxies and empties into voids. In some cases, they've even caught glimpses of proto-galaxies, infant star systems still in the process of forming, their gas halos backlit by the quasar's brilliance. And occasionally, the lines betray something stranger: gigantic clouds of gas hurtling through intergalactic space, ejected by the fury of ancient quasar winds or galactic collisions. Perhaps most astonishing is what these time capsules say about the universe's evolution. Heavy elements carbon, silicon, iron show up in absorption lines far earlier than predicted, suggesting the first stars forged and scattered these materials with breathtaking speed. Other lines reveal how the universe's opacity changed over time, tracing the epoch when ultraviolet light from quasars and young galaxies ripped electrons from atoms, ending the cosmic dark ages. Without quasars as our backlights, these chapters of cosmic history would remain written in invisible ink. Yet the story isn't just about the past. Quasar absorption lines also probe the here and now, uncovering rogue gas clouds in our own galactic neighborhood or the mysterious missing baryon problem, where a significant fraction of the universe's normal matter has seemingly vanished. The answer, it might be hiding in diffuse million-degree gas, detectable only when a quasar's light shines through it. In the end, quasars are more than luminous monsters. They're the universe's scribes, etching its autobiography in light and shadow. Every spectrum is a page, every absorption line a sentence, and with each observation, we learn to read a little more of the story. Among the universe's most violent spectacles, few match the raw fury of a blazar, a quasar with its particle jet aimed like a cosmic gun barreled straight at Earth. Unlike their quasar cousins, whose jets point harmlessly into the void, blazars bombard us with energy so intense it dwarfs the entire output of our sun compressed into seconds. These aren't just bright objects, they're celestial flashbulbs capable of unleashing gamma-ray flares 1 trillion times more energetic than visible light. And the closer we look, the more their behavior defies explanation. The heart of the mystery lies in those jets. Standard models suggest they should emit energy predictably, synchrotron radiation from electrons spiraling in magnetic fields. But blazars laugh at standard. Their gamma-ray flares spike so abruptly, sometimes doubling in brightness in minutes, that conventional physics struggles to keep up. For particles to radiate at these energies, they'd need to accelerate faster than any known natural process allows. It's as if the universe has a hidden particle accelerator, one that makes the Large Hadron Collider look like a toy. One radical theory points to magnetic reconnection, a process where tangled magnetic fields snap and realign near the black hole, unleashing bursts of energy like cosmic short circuits. Picture a rubber band stretched to its limit, then suddenly released, flinging particles outward at near light speed. Another idea involves shocks within the jet itself, where supersonic turbulence acts like a cosmic pinball machine, slamming particles to ever higher energies. But even these explanations fall short when confronted with the sheer violence of blazar flares. The real enigma: some blazars emit too much high-energy radiation. According to basic physics, gamma rays produced near the black hole should collide with lower-energy photons, annihilating each other before they escape. Yet somehow, these photons reach us unimpeded. This gamma-ray transparency problem hints at gaps in our understanding of jet structure. Perhaps the particles are accelerating far from the black hole, in regions where photon collisions are rarer. Or maybe space-time itself twists the jet into a helix, creating escape routes for gamma rays that shouldn't exist. Then there's the question of scale. Blazar jets stretch millions of light-years, yet their most violent flares seem to originate in regions no larger than our solar system. How can something so compact generate such explosive variability? Some astronomers speculate the answer lies in relativistic beaming, where the jet's near-light-speed motion focuses radiation into a narrow cone, like a lighthouse beam intensified by a cosmic magnifying glass. But even this can't fully explain the rapid flickering, suggesting microstructures within the jet, clumps or shocks that amplify brightness in fleeting, localized bursts. What's clear is that blazars aren't just quirks of orientation. They're extreme laboratories testing the limits of particle physics and black hole dynamics. Every flare challenges our models, pushing us toward stranger theories like quantum effects near the event horizon or dark matter interactions. And with each observation, we're reminded the universe's most dazzling monsters are also its most reluctant teachers, revealing their secrets one gamma-ray flash at a time. Sometimes the universe plays tricks on light and our eyes. When a distant quasar's beam passes near a massive galaxy on its way to Earth, the intervening galaxy's gravity bends the light like a cosmic funhouse mirror. The result, a single quasar appears as multiple, distorted copies scattered across the sky, ghostly mirages of the same object flickering in perfect synchrony. These aren't just optical illusions. They're some of the most stringent tests of Einstein's general relativity ever devised, and they're revealing secrets about the invisible scaffolding of the cosmos. Take the famous Einstein cross, a quasar whose light has been split into 4 ghostly images, arranged around a foreground galaxy like points on a compass. Each image follows the same brightness variations, but with slight time delays because the light takes different paths around the galaxy's gravitational well. By measuring these delays down to mere days, astronomers have clocked the expansion rate of the universe with precision. But there's a catch. The delays don't always match predictions, hinting at hidden complexities in how mass, especially dark matter, is distributed within the lensing galaxy. The distortions can get even wilder. When the alignment is just right, the quasar's light stretches into a complete circle, an Einstein ring where the background object wraps perfectly around the foreground mass like a fiery halo. These rings aren't just stunning, they're cosmic scales weighing the lensing galaxy's total mass, including its dark matter halo. Some rings even show kinks or twists, betraying the presence of satellite galaxies or clumps of dark matter too faint to see directly. It's as if the universe handed us a gravitational X-ray machine, exposing its hidden structures. But the real shock came when astronomers realized these lensed quasars could flicker out of sync. Normally, identical light paths should vary in unison. Yet in systems like JWST J100, 4 + 4 112, one image brightens while another dims, a discrepancy that could rewrite our models of dark matter. One theory suggests ultra-dense dark matter, microhalos, are warping space-time on small scales, creating extra lensing effects. Another proposes rogue black holes drifting unseen through the lensing galaxy, their gravity adding chaotic wrinkles to the light's path. Beyond testing relativity, these cosmic mirages serve as natural telescopes. The lensing effect magnifies quasars that would otherwise be too faint to study, revealing details like their host galaxies or the structure of their accretion disks. In rare cases, they've even caught quasars in the act of flickering, letting astronomers map changes in brightness across the disk itself, like watching a strobe light through a kaleidoscope. Yet for all their utility, lensed quasars remain fiendishly rare. Only 1 in 500 quasars gets perfectly aligned for such dramatic effects. Finding them requires combing through millions of galaxy surveys, often with machine learning algorithms trained to spot the telltale symmetry of multiple images. And each new discovery brings fresh puzzles. Why do some lenses produce more images than others? How do tiny fluctuations in the lensing galaxy's mass distribution tweak the observed time delays? The answers could redefine everything from dark matter's nature to the universe's expansion rate. Because when light bends, it doesn't just create pretty pictures, it sketches a blueprint of the cosmos, dark matter and all, written in the warped glow of quasars billions of years old. Peering through telescopes, astronomers sometimes catch what looks like a cosmic dance, 2 quasars, side by side, flickering in eerie harmony. At first glance, it seems like a rare binary system, 2 supermassive black holes locked in a gravitational waltz. But looks can deceive. Many of these pairs are illusions, either gravitational mirages bending light from a single quasar into multiple images, or chance alignments where unrelated quasars happen to line up from our vantage point. This cosmic sleight of hand isn't just a curiosity. It's a puzzle that scrambled our understanding of quasar clustering and the large-scale structure of the universe. Gravitational lensing is the usual suspect. When a massive galaxy or cluster sits between us and a distant quasar, its gravity warps space-time, splitting the quasar's light into multiple images. These duplicates often appear symmetrically around the lensing object, like reflections in a broken mirror. But sometimes the alignment is so precise that the lens itself remains invisible, leaving only the twin quasars visible. The telltale sign: identical spectra and synchronized brightness variations, smoking guns proving it's the same object, just seen multiple times. Then there's the chaos of projection effects. In a universe crammed with quasars, some inevitably line up by pure chance, separated by vast distances but appearing cozy neighbors in the sky. These imposter pairs are far trickier to unmask. Unlike lensed quasars, their spectra differ and their light curves don't sync. Yet even here, the universe plays dirty. Occasionally, two unrelated quasars, one nearby, one far away, show similar redshifts due to the Doppler effect of their motion, masquerading as a true binary. The stakes are high. Real binary quasars are gold mines for studying black hole mergers and galactic evolution. But false positives muddy the waters, inflating estimates of quasar pairing rates and distorting maps of cosmic structure. To weed out the fakes, astronomers deploy a forensic toolkit: high-resolution imaging to spot lensing galaxies, time delay measurements to catch synchronized flickering, and spectroscopy to compare chemical fingerprints. Even then, some cases defy certainty. The most notorious example, JWST J101 7+05425, a pair so perfectly matched it was hailed as the first confirmed binary quasar. Until deeper observations revealed a faint lensing galaxy hiding in the glare, the discovery forced a reckoning. Up to a third of binary quasars might be mirages. Yet this confusion isn't just a hurdle, it's a clue. By studying these illusions, we're learning how matter, especially dark matter, is distributed across the cosmos. Every false pair unmasked sharpens our models of the universe's invisible scaffolding, and sometimes the truth is stranger than fiction. In rare cases, lensing creates not just doubles but quasar triplets or even quadruplets, like celestial doppelgangers frozen in a hall of mirrors. These multiply imaged quasars are more than cosmic oddities. They're stress tests for relativity, probes of dark matter's granularity, and reminders that in the universe's grand illusion, even the brightest beacons can't always be taken at face value. For quasars, death isn't always a slow fade. It can be a cosmic light switch, flicked off in what feels like an instant. Astronomers call this phenomenon AGN flickering, and it's one of the most dramatic exits in the universe. Picture a quasar shining brilliantly for millions of years, its black hole feasting on gas and dust until suddenly the buffet runs dry. Without warning, the accretion disk empties, the jets sputter out, and the once dazzling beacon winks into darkness. What's left? A supermassive black hole, now dormant, lurking silently in the heart of a galaxy like a sleeping dragon. But catching this shutdown in action is like trying to photograph a thunderclap. It's fleeting, violent, and brutally hard to predict. Theories abound about what triggers this sudden starvation. One leading idea points to chaotic feedback mechanisms. As quasars devour matter, their radiation and particle winds blast outward, pushing away the very gas that feeds them. It's a self-destruct sequence. The more the quasar eats, the more it scatters its future meals. In some cases, these winds might clear out an entire galactic center in less than 100,000 years, a blink in cosmic time. Another possibility involves mergers. When galaxies collide, gravitational chaos can funnel gas directly into the black hole's maw, or yank it away entirely like a tablecloth jerked from under a feast. The real challenge is witnessing this shutdown live. Since light takes time to travel, we're often seeing quasars as they were billions of years ago. But recently, telescopes have spotted something peculiar. galaxies where the quasars' on and off states are both visible, like a cosmic before and after shot. In one case, a quasar's jets appeared to slam into a wall of gas, triggering a shock wave that ricocheted back and choked off the inflow. In another, a black hole's X-ray emissions dimmed by a factor of 10,000 in under a decade, suggesting its accretion disk evaporated almost overnight. These observations hint at a startling truth: quasars might flicker on and off repeatedly over their lifetimes like a faulty neon sign. Some could even be reborn, reigniting when fresh gas drifts too close. If so, our census of dormant black holes might be missing countless ghosts of past quasars, their brilliance faded but their hunger undiminished. The hunt for flickering AGN is now a race against time. New telescopes like the Vera Rubin Observatory are scanning the skies for sudden drops in quasar brightness, while X-ray observatories probe for the telltale silence of a black hole's last meal. Every shutdown caught in action is a clue, not just to how quasars die, but to how galaxies lose their voices, fading from radiant giants to silent shadows in the cosmic dark. Imagine the universe as a fog-shrouded landscape just a few 100 million years after the Big Bang. Light barely travels, not because it's dark, but because space itself is opaque, choked with dense hydrogen gas that greedily soaks up every photon. This was the cosmic dark age, an era when stars had barely flickered to life and galaxies were mere infants. Then something extraordinary happened. The fog lifted, space became transparent, and the cosmic architects behind this transformation, quasars blazing through the early universe like torches in the void, their radiation powerful enough to strip electrons from atoms and tear apart the very fabric of the primordial gloom. This process, called reionization, wasn't gentle. It was a cosmic cataclysm. As quasars flickered on, their ultraviolet light bombarded neutral hydrogen atoms, each photon packing enough energy to rip an electron clean off its nucleus. Over millions of years, these photon bullets drilled through the fog, creating growing bubbles of ionized gas where light could finally travel freely. The universe, once a murky swamp, became a crystal-clear ocean. But here's the catch: reionization wasn't instant. It was patchy, uneven, a mosaic of clearing and chaos. Early quasars carved out the first transparent regions like pioneers blazing trails through an uncharted wilderness, while pockets of stubborn hydrogen clung to their neutrality, only to surrender later under the assault of younger quasars and galaxies. The evidence lies in the oldest light we can see: the cosmic microwave background. Its polarization patterns reveal reionization's fingerprints, showing how and when those first ionizing photons did their work. But quasars didn't act alone. Their radiation was so intense, it likely supercharged the process, ionizing hydrogen far beyond their immediate surroundings. Some models suggest a single quasar could clear a volume of space millions of light years across, its UV beams acting like a cosmic sandblaster. Yet paradoxically, quasars were rare in the early universe. How did so few manage to reionize everything? The answer might lie in their efficiency. Unlike early stars, which emitted ionizing photons only to have them absorbed by nearby gas, quasars' radiation traveled vast distances, punching through gas clouds that would have stifled smaller sources. But reionization wasn't just about clearing the fog. It set the stage for everything that followed. Without it, modern telescopes would see nothing, the universe's history obscured behind a curtain of neutral hydrogen. Quasars didn't just light up the cosmos, they made it visible, etching the conditions for galaxies to evolve and light to weave the tapestry we now observe. And in their afterglow, they left another puzzle, echoes of their violence in the form of helium ions, twice as hard to ionize as hydrogen. The fact that we see fully ionized helium in the early universe hints that quasars' energy output wasn't just prodigious, it was precise, fine-tuned to alter the cosmos on scales we're only beginning to fathom. Yet mysteries linger. Why did reionization take hundreds of millions of years to complete? Were quasars the dominant players, or did early galaxies contribute equally? And how did the first black holes grow massive enough to power quasars so quickly? Each answer peels back another layer, revealing how these cosmic titans didn't just shine. They sculpted the universe into the transparent, luminous expanse we call home. Deep in the heart of a quasar's spectrum, astronomers sometimes stumble upon spectral lines that should be impossible lines emitted by atoms under conditions so extreme they defy the very laws of physics as we know them. These are the forbidden emission lines, ghostly signatures of chaos, where the rules governing atomic behavior break down under the sheer brutality of quasar environments. Normally, atoms emit light when electrons jump between energy levels, but quantum mechanics dictates strict rules for these transitions. Some jumps are so unlikely, they're practically forbidden, hence the name. Yet quasars don't just bend these rules, they shatter them, producing forbidden lines with shocking intensity. The reason? An environment so violent, so alien, it forces atoms into states nature never intended. Take the classic case of oxygen atoms in a quasar's broad line region. Under normal conditions, a specific transition in doubly ionized oxygen, labeled O-3, is so improbable it's barely detectable. But in quasars, this forbidden line blazes brighter than many allowed lines, screaming its presence across the cosmos. The explanation lies in the density, or rather, the lack of it. In everyday settings, atoms collide so frequently that forbidden transitions get smothered before they can occur. But in the thin, frenzied gas near a quasar's core, atoms might go seconds or even minutes between collisions, an eternity in atomic time. This lets electrons linger in precarious states long enough to make the impossible jumps, unleashing forbidden light with eerie persistence. Yet some quasars take this defiance further. Their spectra reveal lines that shouldn't exist even in low-density environments, transitions so forbidden they require conditions beyond textbook physics. One theory points to magnetic fields strong enough to warp electron orbits, twisting quantum probabilities into knots. In the grip of a quasar's magnetic fury, electrons might tunnel through energy barriers that would otherwise block their path, like a ghost walking through walls. Others suggest relativistic effects, atoms moving at near light speed, their electrons distorted by time dilation, emitting light that carries the scars of distorted spacetime. The most tantalizing cases involve lines that flicker unpredictably, vanishing and reappearing faster than light could cross the emitting region. This implies structures smaller than our solar system, perhaps clumps of gas caught in the black hole's gravitational jaws, where tidal forces shred matter into filaments so tenuous they're practically transparent. Here, forbidden lines become cosmic diagnostics, probing densities so low they mimic the vacuum of intergalactic space, yet temperatures so high they rival the sun's core. It's a realm where atoms are simultaneously fried and frozen, stretched and squeezed, their electrons pushed to the brink of rebellion. And then there are the doubly forbidden lines, transitions so improbable they make regular forbidden lines look mundane. These ultra-rare emissions, like the mythical Phi-X line from highly ionized iron, demand conditions so extreme they're almost theoretical. Gas so hot it's stripped down to bare atomic nuclei, yet somehow still managing to emit light. Detecting these lines is like finding a whisper in a hurricane, yet quasars deliver them with startling clarity, forcing us to rethink how matter behaves at the edge of annihilation. What's clear is that forbidden lines aren't just quirks, they're distress signals from atoms trapped in the universe's most punishing environments. Each one is a clue, pointing to magnetic fields stronger than neutron stars, densities lower than lab vacuums, or velocities that brush against the cosmic speed limit. By decoding them, we're not just studying quasars, we're stress-testing physics itself, prying open cracks in our theories where the universe's strangest secrets spill through. Among the countless quasars blazing across the cosmos, A handful stand apart, enigmas so rare they defy categorization, like celestial unicorns galloping outside the herd. These outliers possess traits that shouldn't exist: black holes spinning backward, quasars missing their signature broad emission lines, or even ones that flicker with rhythms no model can explain. They're not just oddballs, they're rebels rewriting the rules of quasar physics with every anomalous pulse of light. Take the case of quasars lacking broad emission lines, a feature so fundamental to their identity that their absence seems impossible. Normally, the frenzied gas near a quasar's black hole produces wide, turbulent emission lines in its spectrum like fingerprints of chaos. But a rare few, dubbed naked quasars, show only narrow lines, as if their inner maelstrom has been mysteriously silenced. One theory suggests these quasars are viewed precisely pole-on, their accretion disks angled like a dinner plate facing us, hiding the turbulent broad-line region from sight. Another possibility: their black holes are starving, their accretion disks so thin and anemic they can't generate the usual tumult. Either way, their existence forces astronomers to ask, have we misclassified entire populations of quasars simply because we're seeing them from the wrong angle? Then there are the spin paradoxes. Most supermassive black holes rotate in the same direction as their accretion disks, like a whirlpool spinning with the current. But a handful exhibit retrograde spin, rotating backward against the flow of incoming matter. This cosmic mismatch creates a gravitational tug-of-war where the black hole's spin fights the disk's motion, generating bizarre effects. Simulations show these rebellious spins can produce jets more powerful than their orderly counterparts, as if the black hole's defiance fuels extra fury. Some even suspect these mavericks might be the product of chaotic mergers, where two black holes with opposite spins collided and left a twisted remnant behind. But the strangest unicorns of all might be the changing-look quasars, objects that transform their entire spectral identity over mere years. One moment, they're classic quasars with blazing broad lines. The next, those lines vanish, leaving behind a spectrum indistinguishable from an ordinary galaxy. The leading explanation: a sudden, catastrophic disruption in the accretion disk. Perhaps a star strayed too close and was shredded, temporarily choking off the flow of gas. Others propose that magnetic instabilities flip a switch in the disk structure, shutting down the broad line region like a cosmic dimmer. Whatever the cause, these shape-shifters blur the line between quasars and ordinary galaxies, suggesting the difference might just be a matter of timing and perspective. The rarest of all might be the silent quasars, objects with all the X-ray and radio signatures of a classic quasar, but no visible light to speak of. These phantoms hint at thick shrouds of dust cocooning the central engine so completely that only the highest energy radiation escapes. Finding them is like hearing a scream through a soundproof wall. You know the violence is there, but the details are muffled. Some astronomers wonder if these could be quasars in their infancy or twilight years, their growth stunted or their fuel reserves nearly spent. What unites these outliers isn't just their strangeness, it's the way they expose the limits of our cosmic taxonomy. Like biologists discovering a mammal that lays eggs, astronomers are forced to confront the uncomfortable truth: the universe doesn't care about our classification schemes. Every unicorn quasar is a reminder that for every rule we write, the cosmos has an exception waiting in the shadows, ready to upend our understanding once again. At first glance, quasars seem like cosmic wrecking balls, violent monsters that should tear their host galaxies apart. With winds blasting at thousands of kilometers per second and radiation fierce enough to strip planets bare, they possess all the subtlety of a supernova in a china shop. Yet hidden in this fury is a paradox. These same destructive forces can create as readily as they destroy, sculpting galactic ecosystems with a precision that defies expectation. Welcome to the enigma of AGN feedback, where quasars play dual roles as both executioners and midwives in the story of star formation. picture a massive galaxy rich with gas, the raw material for new stars. In one scenario, a quasar awakens at its core, unleashing winds so powerful they sweep entire molecular clouds out into the void. These outflows act like cosmic bulldozers, clearing neighborhoods of star-forming fuel and leaving behind sterile galactic deserts. We see this in red and dead elliptical galaxies, where quasars likely shut down star formation billions of years ago, their gas reservoirs exiled beyond retrieval. The numbers are staggering. A single quasar outburst can eject thousands of solar masses of gas annually, starving its host galaxy of future generations of stars. But here's where the paradox deepens. In other galaxies, quasars appear to trigger star formation, not quench it. Their outflows slam into surrounding gas clouds, compressing them like snowplows piling up drifts. The shockwaves heat the gas, but in doing so, they also increase its density, creating pockets cool enough for hydrogen atoms to clump together. Suddenly, what was a diffuse cloud becomes a stellar nursery, bursting with newborn stars. This duality is etched into galaxies like Messier 82, where a central AGN's fury has ignited a starburst so intense it outshines the rest of the galaxy combined. The key lies in the balance between chaos and order. Quasar winds are not uniform. They're chaotic, fractal, laced with turbulence that determines whether gas is lost forever or merely reshuffled. Close to the quasar, radiation vaporizes molecules, sterilizing the immediate vicinity. But farther out, the same energy can sculpt gas into dense shells and filaments, priming it for collapse. It's like a wildfire, devastating to the underbrush, yet clearing space for new growth. Even more intriguing is the role of time. Quasars might flicker on and off over millions of years, their feedback alternating between destructive and constructive phases. Early in a galaxy's life, violent outflows could regulate growth, preventing the black hole from gorging itself too quickly. Later, weaker bursts might nudge remaining gas into forming stars at a steadier pace. This stop-start rhythm could explain why some galaxies show evidence of both quenched and starburst episodes in their histories, like trees bearing rings of drought and plenty. The biggest mystery: how much of this feedback is necessary? Some simulations suggest galaxies require quasars to avoid overheating. Without their outbursts, gas would overcool, forming stars so prolifically that galaxies would burn out before reaching maturity. In this view, quasars aren't just bystanders in galactic evolution. They're regulators, acting like cosmic thermostats to maintain equilibrium. Yet other models argue feedback is more capricious, its effects swamped by mergers or dark matter dynamics. The truth likely lies in between. Quasars are neither angels nor demons, but forces of nature capable of destruction and creation in the same breath. Their feedback loops weave through galaxies like invisible threads, pulling some regions taut with star birth, leaving others slack and barren. And in this delicate tug of war, they shape not just individual galaxies, but the large-scale structure of the universe itself, one turbulent gust at a time. Quasars do more than dazzle. They act as cosmic detectives, exposing the universe's most elusive fugitive, dark matter. As their light journeys across billions of light years, it doesn't travel unimpeded. Invisible masses, clumps of dark matter, warp space-time along the way, bending the quasar's light like a funhouse mirror. These subtle distortions, called weak gravitational lensing, imprint faint ripples on the quasar's image, betraying the presence of matter we can't see. It's as if the universe leaves fingerprints on light itself, and quasars are the flashlights that illuminate them. The real magic happens when astronomers study thousands of quasars at once. Each distorted image acts like a pinprick in a cosmic map, tracing the scaffolding of dark matter filaments that weave the universe into a vast, interconnected web. Some of these filaments stretch hundreds of millions of light years, funneling galaxies into clusters and leaving voids nearly empty. Without quasars backlighting this hidden architecture, we'd be blind to the universe's true structure. But here's where it gets stranger. The distortions don't always match predictions. Some dark matter clumps appear more concentrated than models allow, while others seem suspiciously absent, hinting that dark matter might be more complex than a single sluggish particle. Quasars also test the boundaries of gravity itself. When their light bends around massive galaxy clusters, the amount of deflection sometimes exceeds Einstein's predictions. Could this mean dark matter isn't the culprit, but that gravity behaves differently on cosmic scales? Alternative theories like modified Newtonian dynamics propose tweaking gravity's equations instead of invoking invisible matter. But quasars deliver a knockout punch to these ideas. Their lensing patterns often require more unseen mass than even dark matter models predict, leaving modified gravity theories scrambling. The most tantalizing clues come from quasars lensed by nothing at all, patches of space where light bends despite no visible galaxy or cluster in sight. These dark lenses suggest rogue clumps of dark matter drifting between galaxies, untethered to stars or gas. Some might be primordial black holes, remnants of the universe's birth. Others could be evidence of dark matter's cold versus warm varieties, moving sluggishly or zipping through space. By combining quasar lensing with simulations, astronomers are piecing together dark matter's role in cosmic evolution. Did it dictate where galaxies formed? How did it shape the universe's expansion? Each distorted quasar image is a time capsule, preserving snapshots of dark matter's influence over billions of years. And as telescopes grow sharper, these cosmic lighthouses continue to probe the invisible, revealing a universe far stranger and far richer than we ever imagined. Stretching across billions of light years, the light from a quasar doesn't reach us unscathed. Instead, it carries a cryptic message, a tapestry of dark lines etched into its spectrum like scars from battles fought in the void. This is the Lyman Alpha Forest, not a collection of trees, but an intricate web of hydrogen gas clouds that have absorbed specific wavelengths of the quasar's light along its journey. Each line represents a snapshot of the universe's skeleton, a fleeting encounter with the diffuse gas that weaves galaxies together into the cosmic web. The magic lies in the patterns. Unlike the smooth absorption expected from uniform gas, these lines form a forest, dozens, sometimes hundreds, of individual spikes clustered together, each one marking a separate cloud of hydrogen at a unique distance. The farther the light travels, the more stretched and redshifted these lines become, creating a timeline of the universe's expansion. But here's where it gets mesmerizing. The distribution isn't random. The lines cluster in ways that reveal the large-scale structure of the cosmos, vast filaments of gas threading between galaxies, intersecting at nodes where galaxy clusters loom like dense metropolises. It's as if quasars hand us a 3D map of the universe's hidden architecture, written in the language of missing light. What's even stranger is what these clouds tell us about the universe's adolescence. The density of the forest changes with redshift, growing thicker as we look back in time. In the early universe, space was crammed with diffuse hydrogen, and quasars' light barely made it through the fog without being absorbed. But as eons passed, the same gas was ionized, stripped of electrons, by the relentless radiation from galaxies and quasars. The forest thinned, leaving behind only the densest clumps. This transition wasn't smooth. Some regions cleared early, others stubbornly clung to their neutrality, and the forest's evolution now serves as a record of reionization. The universe's awkward phase transition from opaque to transparent. Yet the Lyman Alpha Forest isn't just a relic, it's a dynamic, living structure. Some clouds show signs of turbulence, their lines broadened by supersonic motions as they're pulled by the gravity of dark matter halos or blasted by galactic winds. Others appear unnaturally cold, their atoms barely moving, as if suspended in the quietest corners of intergalactic space. There are even void absorbers, regions so empty they barely register a line at all, marking the desolate stretches where galaxies fear to tread. The real enigma: some of these clouds shouldn't exist. According to simulations, the universe's expansion should have diluted the intergalactic hydrogen into near invisibility. Yet the forest persists, its lines revealing gas far denser than models predict. One explanation points to dark matter's gravitational grip, holding gas in place like cosmic flypaper. Another theory suggests that tiny fluctuations in the early universe's density left behind overdensities that refuse to fade. There's even evidence of filamentary cooling, gas condensing along dark matter threads like dew on a spiderweb, though how it sheds enough heat to do so remains a mystery. And then there are the ghosts Lyman alpha blobs, vast clouds of hydrogen glowing faintly with no obvious source of energy. Some drift near quasars, illuminated by their harsh radiation. Others float independently, lit by the ultraviolet glow of hidden star-forming galaxies, or perhaps even the decay of hypothetical dark matter particles. These blobs might be the nurseries of future galaxies, their gas slowly collapsing under gravity's pull, or they could be the debris left behind by galactic collisions, strewn across the cosmos like cosmic afterthoughts. Deciphering the forest requires more than just telescopes. It demands supercomputers, simulations of cosmic structure formation with their trillions of particles, struggle to reproduce the forest's fine details. The discrepancies hint at gaps in our understanding of gas physics, dark matter behavior, or even the nature of gravity itself. Every quasar spectrum is a Rosetta Stone, and the Lyman alpha forest is its untranslated hieroglyphs waiting to reveal how the universe grew from a smooth soup of particles into the intricate web we call home. But the most profound revelation might be this: the forest isn't just an artifact of distant quasars. It's all around us. The same filaments that absorb a quasar's light 12 billion years away also pass through our local galactic neighborhood. We're floating in an ocean of tenuous hydrogen, part of the same cosmic web that the Lyman alpha forest so vividly maps. In the end, those absorption lines aren't just traces of faraway gas, they're mirrors, reflecting the universe's grand design in the faintest whispers of missing light. Galaxies aren't the solitary islands we once imagined, they're cosmic crash zones, where collisions ignite the most violent fireworks in the universe. And at the heart of these wreckage-strewn battlefields, quasars often awaken, their supermassive black holes roaring to life as if stirred by the chaos around them. Hubble's sharp eye has captured these cataclysmic births in stunning detail. Galaxies twisted into pretzel-like shapes by gravitational tides, their spiral arms shredded into luminous streamers, while at their cores bright new beacons of fury. These aren't just pretty pictures, they're snapshots of a fundamental truth: quasars don't just exist in galaxies, they're born from them, forged in the furnace of galactic violence. Take the iconic antennae galaxies, a pair of spirals locked in a slow-motion train wreck. As their stars and gas swirl into chaos, vast rivers of matter funnel toward their centers, feeding the once dormant black holes lurking there. The result, a brilliant quasar flaring to life like a match struck in the dark. But this isn't instant. The process can take millions of years as gravity reshapes the galaxy's structures, steering gas into the central core. Simulations show these mergers create torque-twisting forces that rob gas of its angular momentum, forcing it inward. It's like stirring a drain with a spoon, accelerating the inevitable plunge. What's striking is how efficient these collisions are at igniting quasars. Isolated galaxies often struggle to feed their black holes' gas orbits stubbornly, refusing to fall in. But a merger, that's a cosmic blender, churning orderly disks into turbulent storms where gas collides, cools, and cascades toward the center. Infrared telescopes have caught this process red-handed, spotting buried quasars glowing through thick dust, the telltale sign of a black hole's feast beginning behind the scenes. And sometimes the violence doesn't stop at one quasar. In systems like NGC 624, two supermassive black holes light up simultaneously, each gorging on gas from the shattered galaxy around them. Yet the most revealing clues come from quasars caught mid-eruption. Hubble's images of Markarian 231 show a galaxy so distorted by a recent collision, its core blazes with the unmistakable glare of a newborn quasar, while tidal tails of ejected stars stretch into the void like cosmic graffiti. These post-merger quasars tell us something profound. The brightest beacons in the universe might owe their existence to the darkest of Dance's galaxies intertwining, their gravity orchestrating destruction and rebirth in the same act. But here's the twist: not every collision sparks a quasar. Some mergers fizzle, their gas exhausted or ejected before the black hole can awaken. Others produce starbursts instead, their material birthing stars rather than feeding the central monster. The difference might lie in the merger's angle, speed, or even the black hole's own appetite. And sometimes the quasar flickers briefly before fading, as if the universe teased us with a glimpse of its power before snuffing it out. These galactic pileups do more than create quasars, they shape the destiny of entire galaxies. By funneling gas inward, they can starve future star formation, leaving behind red and dead ellipticals. Or, paradoxically, they might trigger starbursts in their outskirts, where shockwaves compress gas into new stellar nurseries. The aftermath of a quasar's birth is written in the galaxy's structure for billions of years, a scar that never fully fades. What's certain is this: without galactic collisions, the universe would be far darker. The brightest quasars, those titans from the cosmos's youth, likely owe their brilliance to an era when galaxies crashed together in a frenzy, their chaos birthing the light that now guides our understanding of the deep past. Every time Hubble spots another distorted galaxy with a gleaming core, we're witnessing the universe's most violent poetry: destruction giving birth to illumination, chaos crafting the beacons that pierce the dark. For every quasar blazing across the cosmos, there's a shadowy twin lurking in the dark, cloaked behind curtains of dust so thick, not even visible light can escape. These are obscured active galactic nuclei, the universe's hidden monsters, their brilliance muffled like a scream trapped behind soundproof glass. While traditional telescopes see only emptiness, infrared and X-ray vision reveals the truth: a searing core buried alive, its light absorbed and irradiated as heat, leaking through the cracks in its dusty prison. These ghosts account for nearly half of all supermassive black hole activity, rewriting the story of how galaxies grow and why we've been missing half the cast. The hunt for obscured AGN began with a cosmic discrepancy. Surveys of the early universe found far fewer quasars than models predicted, until astronomers realized we weren't seeing the full picture. Dust, especially in gas-rich young galaxies, doesn't just dim quasars, it erases them entirely from optical surveys. Enter Spitzer and Webb, infrared telescopes that catch the thermal glow of dust heated to hundreds of degrees by the hidden quasar within. Meanwhile, X-ray observatories like Chandra pierce through the haze, detecting high-energy photons that punch through dust like bullets through fog. Combine these views and an invisible population emerges: black holes thriving in secrecy, their growth sprees hidden from plain sight. The most extreme cases push the limits of physics. Some Compton-thick AGN are buried behind column densities so high, even X-rays struggle to escape. Only 1 in a million photons makes it out, the rest absorbed or scattered into oblivion. To detect these phantoms, astronomers rely on reflected X-rays, like listening for an echo in a cavern, or delicate molecular tracers like hydrogen cyanide gas, excited by the quasar's muffled fury. The reward: black holes growing exponentially in conditions we once thought impossible. Their obscuration so complete it reshapes our senses of cosmic power sources. Why does dust hide so many quasars? The answer lies in their feeding habits. As gas spirals toward a black hole, friction generates immense heat and radiation. which, ironically, can blow away nearby dust, creating a visible quasar. But if the inflow is too rapid or the galaxy too rich in gas, fresh dust continually replenishes the shroud. It's a cosmic feedback loop. The more the black hole eats, the more material surrounds it, creating a self-sustaining veil. Some obscured AGN may represent brief, violent phases like a stellar cocoon before they emerge as classical quasars. Others might stay buried indefinitely, their light never breaking free. The implications ripple across cosmology. If half of supermassive black holes are growing unseen, our models of galaxy evolution need serious revision. Obscured AGN could explain mysterious infrared backgrounds or the missing black hole precursors in the early universe. Their winds might even enrich intergalactic space with heavy elements unseen but vital. Most tantalizing, these hidden giants could be the true powerhouses behind ultra-luminous infrared galaxies, objects once thought powered by starbursts, but now suspected to harbor quasars in witness protection. Peeling back the dust reveals another paradox. Obscuration isn't just a barrier, it's a window. The dust itself encodes the quasar's history, its composition, temperature, and motion betraying the violence below. Polarized light sneaking through cracks traces magnetic fields stronger than neutron stars, and the delay between an X-ray flare and its infrared echo maps the dust's geometry like sonar probing a submarine's hull. Even the dust's survival is a puzzle. At temperatures that should vaporize it, something, perhaps microclumping or magnetic armor, keeps it intact under the quasar's withering glare. The final twist: some obscured AGN aren't hidden at all, we're just seeing them from the wrong angle. Viewed edge on through their host galaxy's dusty plane, even a brilliant quasar can vanish. Tilt the perspective, and the same object might blaze unobscured. This orientation bias means our quasar catalogs are partly accidents of cosmic geometry, a reminder that the universe's truths often depend on where and how we choose to look. In the end, these dusty enigmas force a humbling realization. The cosmos doesn't perform for our telescopes. Its brightest actors often play their grandest roles offstage, their scripts written in wavelengths we're only learning to read. And with every obscured AGN unmasked, we confront the exhilarating possibility that the universe's greatest shows are still playing to a half-empty house, waiting for our instruments and our imaginations to catch up. Physics has rules, or at least it's supposed to. One of the most unbreakable, the Eddington limit, acts as a cosmic speedometer for black holes, calculating the maximum brightness an object can achieve before radiation pressure overwhelms gravity, blasting away the very material that fuels it. It's like a fire so hot it extinguishes itself by blowing out its own oxygen. Yet scattered across the universe, a handful of quasars laugh in the face of this law, shining up to 10 times brighter than theory allows. These aren't just anomalies, they're cosmic revolutionaries, forcing scientists to ask, do we misunderstand black hole feasts, or is the universe hiding a way to cheat its own rules? Take the quasar S50014+81, a monster beaming with the light of 60 trillion suns. At that luminosity, its radiation should shred incoming gas clouds like a hurricane hitting tissue paper, starving the black hole within centuries. Yet it's thrived for millions of years, feasting at rates that defy all models. How one radical idea suggests super-Eddington accretion, a scenario where gas floods in so rapidly it overwhelms the radiation's pushback like a fire hose forcing water into a blazing inferno. In this chaotic state, matter might pile up faster than it can radiate, creating a traffic jam of particles that temporarily shields the inflow from the quasar's fury. Simulations show these photon bubbles could form in the disk's maelstrom, trapping radiation long enough for extra matter to slip past the event horizon. But there's a catch. Even super-Eddington flows shouldn't sustain such extreme outputs indefinitely, which leads to the second, even wilder possibility. What if we've misjudged how black holes convert matter to energy? Standard physics assumes an efficiency of around 10%, meaning 90% of infalling mass gets swallowed without a trace. Yet some quasars act as if they're running at 30% efficiency or higher, violating energy conservation itself. The solution might lie in the black hole's spin. A rapidly rotating singularity could wrench extra energy from infalling particles via frame dragging, like a cosmic paddle wheel stealing momentum from a river. Alternatively, magnetic fields near the event horizon might act as particle accelerators, extracting energy that would otherwise vanish into the void. The most baffling cases are quasars that flicker above the Eddington limit, brightening and dimming as if toggling some hidden switch. These aren't gradual changes, they're abrupt, sometimes occurring over mere weeks. One explanation points to magnetically arrested disks, where magnetic fields grow so strong they stall accretion, then suddenly snap like overstretched rubber bands, dumping colossal amounts of matter onto the black hole in bursts. It's the cosmic equivalent of binge eating, with the quasar gorging past its theoretical limit before the radiation backlash forces a pause. Yet the ultimate loophole might not involve physics at all, but perspective. Some quasars may appear to violate Eddington not because they're brighter, but because their jets are aimed straight at us, focusing radiation into a narrow beam. Like a lighthouse appearing brighter when its beam sweeps over you, this relativistic beaming could artificially inflate observed luminosities. Even so, this can't explain all super-Eddington quasars, especially those with isotropic emission signatures. The implications ripple far beyond these rule breakers. If black holes can consistently exceed the Eddington limit, it reshapes our timeline for how the earliest quasars grew so massive so quickly. It suggests galaxies might hide dormant black holes far larger than current surveys indicate, their past gluttony masked by temporary physics-defying feasts. And it whispers an even more provocative idea, that in the universe's most extreme environments, the rulebook isn't just bent, it's rewritten daily in the violent glow of quasars that refuse to play by the rules. Among the universe's most peculiar fossils are the so-called green bean galaxies, cosmic relics where long-dead quasars have left behind ghostly imprints, painting entire galaxies in eerie emerald light. These rare objects, some spanning hundreds of thousands of light years, aren't just fading remnants, they're time capsules preserving the final, violent breaths of quasars that once dominated their galactic cores. What makes them extraordinary isn't their size or hue, it's the fact that they glow without an active quasar, as if the universe forgot to turn off the lights after the party ended. The mystery begins with their color. Green beans emit a specific shade of greenish light from ionized oxygen, a spectral fingerprint typically seen in the furious radiation of live quasars. But here's the twist, these galaxies lack the central engine to produce such fury. Instead, their entire interstellar medium has been flash-frozen in a state of ionization, like a snapshot of a quasar's final moments. The leading theory, the quasar didn't fade slowly, it shut off abruptly, leaving behind a cooling wave of energy that still ripples through the galaxy's gas, lighting it up like a neon sign long after the power's been cut. Scale is another enigma. A typical quasar's ionization zone might stretch a few thousand light-years around its core. Green beans, by contrast, glow across regions dwarfing the Milky Way, their oxygen-lit bubbles expanding far beyond any known quasar's reach. This suggests their former quasars weren't just bright, they were freakishly powerful, perhaps undergoing super-Eddington outbursts that flooded their galaxies with radiation at levels we've never observed directly. Or maybe the gas in these galaxies is unusually sparse, allowing ionization fronts to propagate unchecked, like a wildfire racing through dry grass. The most famous example, JWST spans a staggering 200,000 light-years, a green phantom lingering in the void. Its light profile reveals concentric shells of ionization, like tree rings marking the quasar's death throes. By studying these layers, astronomers can backtrack the quasar's shutdown timeline. The verdict: it didn't sputter out. It snapped off, possibly in less than 50,000 years, a geological heartbeat. What could silence a quasar so swiftly? A merger might have disrupted the accretion disk, or perhaps the black hole simply gulped down its last meal and choked on the aftertaste. Yet green beans aren't just about the past. They're laboratories for understanding feedback, the process by which quasars sculpt their galaxies. In life, a quasar's radiation blows away star-forming gas, sterilizing its surroundings. But in death, the green bean phase represents a fleeting window where that same gas, no longer heated by the quasar, begins to cool and clump. Some models suggest these galaxies are on the cusp of a starburst, their ionized gas ready to collapse into newborn stars once the last echoes of the quasar fade. It's a cosmic metamorphosis, the death of a monster birthing the seeds of new life. The rarest green beans show even stranger behavior. A handful flicker weakly, as if their central black holes are stirring from hibernation, snacking on scraps of gas and reionizing patches of the fossilized nebula. These zombie green beans blur the line between active and quiescent, hinting that quasar shutdowns might not be permanent, just long naps between feedings. Others exhibit tangled magnetic fields threading their glowing gas, relics of the quasar's jets frozen in time like lightning trapped in amber. Finding these cosmic fossils is like stumbling upon a Pompeii of the cosmos, a disaster frozen mid-eruption. Every green bean is a Rosetta Stone, translating how quasars shape galaxies long after their light goes dark. And with each discovery, we're reminded the universe doesn't do endings. It does transformations, turning the ashes of one era into the foundations of the next. At the heart of most galaxies, supermassive black holes sit like anchored kings, ruling from their thrones of stars. But sometimes, through violence unimaginable, even kings get dethroned. Picture a black hole weighing billions of suns, not just displaced but catapulted from its galaxy at speeds topping 5 million miles per hour. Dragging a furious quasar behind it like the tail of a cosmic comet. These aren't theoretical oddities, they're runaway quasars, and their existence proves that even the universe's most massive objects can be sent flying by forces beyond comprehension. The culprit: gravity's ultimate recoil. When two supermassive black holes spiral together and merge, the collision doesn't just release energy. It can launch the newborn black hole in the opposite direction, like a gun kicking back after firing a bullet. Einstein's equations predict this. If the merger is lopsided, gravitational waves carry away momentum unevenly, and the remaining black hole gets a violent shove. The numbers are staggering. A typical kick might reach thousands of kilometers per second, enough to escape all but the most massive galaxy's gravitational grip. And as the black hole flees, it doesn't travel empty-handed. Any gas still clinging to it gets compressed and heated, igniting a quasar that blazes defiantly in intergalactic space, far from the stellar metropolis that birthed it. Astronomers first spotted these exiles by accident. The quasar 3C186, for instance, sits 40,000 light-years from its host galaxy's center, its spectrum revealing a black hole moving away at nearly 2,000 kilometers per second. Then there's JWST J0927+2855, nicknamed the Cosmic Cannonball, with a velocity so extreme it's tearing free of its galaxy entirely. But the real smoking gun comes from Hubble observations of Markarian 1018, where a quasar's outflow traces a straight line back to an off-center black hole, like breadcrumbs leading to a crime scene. What's wild isn't just that these black holes move, it's how long their quasars persist. Conventional wisdom said ejected black holes should quickly starve, their accretion disks stripped by tidal forces. Yet some runaways shine for millions of years, suggesting they're dragging entire reservoirs of gas along with them. Simulations reveal why, as the black hole plows through galactic gas, it can scoop up fresh material like a snowplow, funneling it into a new accretion disk. Others might carry their original disks with them, the gas held in place by magnetic fields stronger than anything in our solar system. The aftermath is even stranger. A runaway quasar isn't just a curiosity, it's a wrecking ball. As it flees, its gravity tugs stars from the galactic core, creating a trailing stream of orphaned suns. Its radiation bathes neighboring gas clouds, ionizing them in bizarre patterns no central quasar could produce. And in rare cases, the recoil might trigger a second quasar back in the galaxy if the merger's kick was weak enough to leave some gas behind, now suddenly free to collapse into the vacant center. But the most profound implication is this: runaway quasars could solve the final parsec problem. For decades, physicists struggled to explain how merging black holes overcome the last crucial distance before collision, where friction from sparse gas can't shrink their orbits fast enough. Gravitational recoil provides an answer. If early galaxies hosted multiple black holes, their kicks might have redistributed them, preventing stalls and speeding up cosmic mergers. Every runaway quasar is a testament to the universe's capacity for violence. They remind us that even the mightiest objects are subject to chaos, that gravity's grip isn't absolute, and that sometimes the brightest beacons in the cosmos are those fleeing their own homes, trailing fire as they go. Quasars don't just scream into the void, they leave behind whispers, echoes of their past fury etched into the fabric of space itself. Picture throwing a stone into a still pond. Long after the splash fades, ripples spread outward, carrying a memory of the impact. Now imagine that stone is a quasar's eruption, and the pond is a nebula light years wide, its gas acting like a cosmic recording device. This is the quasar echo effect, where light from ancient outbursts bounces off interstellar clouds, reaching us thousands, or even millions of years after the original explosion. These delayed signals aren't just ghostly curiosities. They're time machines, revealing a quasar's violent mood swings long after the event itself has faded from view. Take the case of Quasar SDSS J1056+0256, where astronomers spotted a peculiar double image in its spectrum. One set of emission lines matched the quasar's current state, but a second, fainter set showed blue-shifted lines, light that had traveled an extra lap around the universe, reflecting off a distant gas cloud before finally arriving at Earth. By measuring the time delay between the direct and echoed light, researchers reconstructed the quasar's outburst history like detectives analyzing a surveillance tape. The verdict: 80,000 years ago, this quasar was 5 times brighter. Its radiation surge so violent it ionized the surrounding cloud in a flash. But echoes aren't just about brightness. They expose a quasar's spectral fingerprint, the exact mix of ultraviolet, X-ray, and visible light it emitted in the past. When Hubble studied the echo around quasar IC 2497, it found traces of an ancient flare rich in helium ionizing radiation, suggesting the black hole temporarily switched accretion modes, perhaps gulping down a star or destabilizing its disk. The cloud's composition acted like a chemical snapshot, preserving the quasar's diet from an era when human ancestors were just mastering fire. The most astonishing echoes come from light-years-long reverberations, where light bounces between multiple clouds, creating a hall of mirrors effect. In one system, a single quasar flare produced 3 distinct echoes, each reflected off clouds at different distances, like a cosmic chorus singing the same note at staggered intervals. By triangulating these delays, astronomers mapped the 3D structure of the nebula with precision, revealing pockets of dense gas and tunnels carved by past quasar winds. What's eerie is how these echoes blur the line between past and present. The light we see today might be from an eruption that occurred before the pyramids were built, yet its fingerprint is only now reaching us. Some echoes even change over time as the reflected light interacts with new structures, offering real-time views of how quasar radiation reshapes its environment. But the grandest implication, echoes might solve the mystery of quasars flickering. If a quasar's brightness swings wildly, but we only see the delayed echoes, we could misinterpret its behavior entirely. It's like hearing an echo in a canyon and mistaking it for a second shout. By untangling these reflections, we're not just studying quasars, we're learning to read the universe's memory, written in light that refuses to fade. Imagine a quasar pulsing like a heartbeat, its brilliance swelling and fading in a rhythm so precise you could set a cosmic clock to it. These aren't random flickers but eerily regular oscillations, some repeating every few years, others over decades. Astronomers call them AGN heartbeat signatures, and they might be the universe's way of revealing black hole duets or accretion disks teetering on the edge of chaos. Take the case of quasar PG 1302-102, whose brightness swings like a pendulum every 5.4 years. This isn't some gentle ebb and flow. Its luminosity spikes by nearly 40% before settling back down, as if something massive is stirring the pot. The leading theory, a second black hole locked in a gravitational dance with the primary, its orbit periodically disturbing the accretion disk. Picture a shark circling a whirlpool, its gravity kicking up waves that slosh onto shore at predictable intervals. Each close pass would funnel extra gas toward the central black hole, igniting a temporary flare before the dance continues. But here's where it gets strange. Some heartbeat quasars don't just oscillate, they drift, their rhythms speeding up or slowing down over time. This rules out simple orbital mechanics. No two-body system should change its tune so abruptly. One explanation points to accretion disks on the brink of instability. Like a pot of water nearing a boil, these disks might alternate between steady and turbulent states, their viscosity shifting as magnetic fields twist and snap. Simulations show these systems can breathe, expanding and contracting in cycles that match observed quasar heartbeats. The wildest possibility, these pulses could be echoes of black hole mergers. When two supermassive black holes finally spiral together, their collision sends gravitational ripples through space-time, but just before the final plunge, their orbits can induce rhythmic kicks to the surrounding gas. Some models suggest heartbeat quasars are cosmic stopwatches, counting down the centuries until a cataclysmic union. We might even be witnessing the precursor to events like the one LIGO detected, but on scales billions of times more massive. Yet the most tantalizing clues come from heartbeat quasars that break their own rhythm. In 2021, OJ287, a previously steady pulsar, suddenly skipped a beat, its 12-year cycle disrupted by an unexplained outburst. Was this a disk instability going rogue, a third black hole muscling into the dance, or something entirely new, like a star falling into the accretion disk and briefly hijacking the rhythm? Every heartbeat quasar is a paradox, a beacon of chaos flickering with unnatural order. Their pulses carry encrypted messages about the most violent partnerships in the cosmos, and decoding them might finally answer how black holes grow, merge, and shape the galaxies they call home. What if quasars aren't natural phenomena at all but cosmic lighthouses built by advanced civilizations? It's a wild idea straight out of science fiction, yet some have seriously proposed that these blazing objects might be artificial beacons, deliberately engineered to broadcast their presence across the universe. Imagine a super-advanced alien society harnessing the power of a supermassive black hole, using it as a gravitational dynamo to send messages or even power interstellar travel. The premise is undeniably thrilling. Instead of chaotic accretion disks, we're seeing precision-designed megastructures, their light patterns encoding alien mathematics or navigation coordinates. The hypothesis isn't entirely baseless. Quasars do emit incredibly focused energy, and their variability could theoretically carry information. Some even pulse in quasi-regular patterns, sparking speculation about intentional signaling. The most provocative argument comes from their sheer efficiency, converting mass to energy with near physical limits, as if optimized by design. Could nature alone create such precise, luminous machines? Proponents point to humanity's own radio transmissions as a parallel. If we're broadcasting our existence, why wouldn't others? But here's where Occam's razor slices through the speculation. For every engineered quasar trait, astrophysics offers a simpler, natural explanation. Those rhythmic pulses, they're likely caused by clumps of matter spiraling into the black hole at predictable intervals, not alien Morse code. The focused jets, a natural consequence of magnetic fields channeling plasma along the black hole's spin axis. Even the efficiency fits known physics. Accretion disks convert mass to energy through well-understood processes, no alien blueprints required. The knockout punch comes from redshift evidence. Quasars follow Hubble's law perfectly, their light stretched by the expansion of the universe exactly as distant galaxies are. If they were artificial beacons, we'd expect some to defy this pattern, perhaps lurking closer, their light unredshifted. Yet every quasar observed aligns with cosmic expansion, placing them billions of light-years away in the ancient universe. Worse for the alien hypothesis, quasars were far more common in the past, peaking when the universe was just a fraction of its current age. Why would civilizations cluster their beacons in the cosmos's youth, then vanish? Then there's the energy problem. Building a quasar-scale transmitter would require dismantling stars for fuel, an engineering feat so absurdly impractical it makes Dyson spheres look like Lego projects. Even if a civilization could harness a black hole, the radiation blasting from a quasar would sterilize nearby space, making it useless as a habitat or communication hub. And why choose a beacon that drowns out all other signals in gamma rays and X-rays? It's like trying to whisper in a hurricane. The irony, while quasars probably aren't alien lighthouses, their existence does make interstellar communication harder. Their radiation floods the cosmos with noise, masking fainter, potentially artificial signals. In a way, they're nature's ultimate jamming devices, drowning out the very whispers we'd need to detect to find extraterrestrial intelligence. So while the idea of engineered quasars is a fascinating thought experiment, the universe offers a far grander truth. Nature, left to its own devices, can outshine even our wildest fantasies. The reality, black holes sculpting spacetime into radiant monsters, needs no embellishment to be awe-inspiring. Quasars are beacons, just not the kind we imagined. They light up the cosmos not with messages, but with the raw, untamed brilliance of physics itself. From the ravenous supermassive black holes devouring suns in a single day to the cosmic mirages bending light across billions of light-years, these 25 bizarre quasar phenomena aren't just astronomical curiosities, they're revolutionaries, tearing up the rulebook of astrophysics one discovery at a time. Each one challenges what we thought possible, whether it's black holes spinning backward, quasars flickering like cosmic strobe lights, or entire galaxies glowing green long after their central engines have shut down. These aren't just distant wonders, they're active puzzles reshaping our understanding of gravity, time, and the very fabric of the universe, and the revolution is just beginning. With telescopes like JWST and the upcoming Vera Rubin Observatory, we're poised to crack open even deeper mysteries. Will we catch a quasar mid-shutdown, watching in real time as a black hole's feast turns to famine? Could gravitational wave detectors uncover the hidden dance of binary quasars, their mergers sending ripples through space-time? Or will we finally spot the elusive, middleweight black holes that could solve the riddle of how these cosmic titans grew so fast? Every new instrument is a key, unlocking doors we didn't even know existed. But here's the real magic. These discoveries aren't just for scientists. They're for anyone who's ever looked up at the night sky and wondered what else is out there. Maybe you're captivated by the forbidden light of atoms pushed to their breaking point. or the way quasars sculpt galaxies into existence even as they tear them apart. Perhaps it's the runaway black holes fleeing their homes like cosmic outlaws that ignite your imagination. Whatever it is, the universe has a way of making the impossible feel personal, turning distant phenomena into stories that resonate. So tell us, which quasar mystery keeps you up at night? The phantom jets that defy physics, or the way these cosmic monsters flicker messages across the ages? Drop your thoughts in the comments, and if you're hungry for more deep space wonders, hit like and subscribe, because the universe isn't done surprising us, and neither are we. The next revelation is always just one observation away, waiting to light up the darkness.